Hello guys, this video is about evolving neural network through augmenting topologies applying in Unity. So imagine you got satellite in the space. So this is my little satellite, and you want to be able to rotate on the own axis as well as travel towards certain direction, and yet be facing some direction, facing some sides, be always certain direction. In this case, I want to be facing or pointing the direction towards the target object. If my target object is changing, its orientation is changing, I would expect my satellite to change. So for example, because I'm trying to make a game, I want this be rotating towards changing, let's say, position of the orbit. So my satellite should go there as well, the same direction, yet keep it spinning same direction. Now, the only trick and much nicer, you could use Lerp function. The Lerp function just to adjust the orientation, make the same orientation. But I wanted to avoid that. I want to avoid the Lerp function because I want to make a simulator which is more closely to the real physics alike. So I assume my little spacecraft reassembled here. You can imagine it got thrusters. This, let's say, on the right, from the right back, left from the back, etc. on top as well. Now if I have front left and the back right propulsion fired at the same time, so of course my satellite should turn this direction. Of course he spies and try to adjust to the orientation of that target, neural network target. So of course you got different orientation involved the satellite, specifically when it turns or rotates along the own axis. Otherwise it shouldn't be that much problem to finding the orientation. But if I spin along my own axis, let's say axis Z, which in this case axis Z, which is there, which is forward axis. Now if I try to change and use the equivalent thrusters, of course I cannot fire the same thruster, because now I fire at a given time, I fire thruster which are on the left side, at some point on the right side, and on top, on the bottom. Of course it's rotated 180 degrees, everything is opposite. So I need to adjust those. That's why I got a bit wobble. More thrusters possibly could make more responsive, or proper, more learned network could be even more responsive. Of course I can change the velocity, how fast I want to rotate, expecting rotate. I want to apply the offset, so it's 90 degrees with the y-axis toward, so that's y-axis which is just there, for my target, 30 degrees or 25.4, whatever the angle of x-axis. Or maybe I want to spin along the x-axis instead of z-axis. I'll add my spin. So now I'm rotating with my own x-axis. Let's say 0.3 if I want to have x and y-axis. And yet be facing z-axis same, I try to have same as this one. Of course now it's a bit difficult because of the general rotation, so it might get a little crazy. Nevertheless, it does work. So what I'm doing here, instead of using the Lerp function, I'm applying the forces into the rigid body. In this case specifically I'm applying the torque, but you can apply as well force pointing at a given position. So I'm using the neural network based on the paper of which source I will show just a moment. So this paper describes the neural networks or genetic evolving neural networks were involved as well mutations of the degenerations. So this neural network is based, the script which I developed is based on the works of the one, and he shows on his channel evolving neural networks need with 3D cars. I was searching number sources, even GitHub, to actually find code or references which I can actually apply for the Unity. It's worth to look at about his channel. He's got his paper reference here and his project is it's just there. If you type that, neural network augmented topologies, you should be able to find so his channel. Got some projects here. They're cool stuff. Look at this guy. Anyway, so angular velocity match script, which I developed based on the template, which is provided with a project, which as well on the video link is described in. So this is a little script which I developed. Basically what's happening, there's the major part. So firstly first, there is rigid body. Add relative torque. I apply the torques to rotate my rigid body, respectively. So the learned system of the brain of the neural networks apply the throttle and the output depends on the orientation of the satellite in respect to the reference and the offsets. So just that. That's how it controls. I said there is no Lerp function. There is one, but I'll give you, I'll get there. So, firstly, what I have here, I got target velocities, so I can change the target velocity, how fast I want to spin. I got target position, my position of the angular position. I can switch between each axis whether I want to use the angular velocity or angular position. I got some just feedback information, position error, current angle and lifetime used of the system. This is disabled at the moment, but generally this is on. Lifetime of the entity is used when the new neural network is generated. Back into the code. So what happened here? I got my rigid body, which is my entity, which is my satellite. I take my angular velocity and I try to calculate the angular velocity, actually angular velocity of the local angular velocity of my space along on axis rather than global. This is the current angular velocity as for the display only, which is just there. Sorry, those parameters. And then you got the parameters when they used or not used, whether not required. Basically, you need to have to all toggle. So I'm expecting that at least two angles not be triggered to be adjusted to the current orientation and spin only around the on axis, one single axis. And what's happening here? So I got target offset, which is my target offset position here, angular position. I calculate my target rotation, so the current target rotation, which is this is my target rotation plus angular offset, this one, it's quaternions multiplied. I'm finding the nearest target rotation. So this target That's the Lerp when it's involved. Basically what it does is I'm taking my current rotation, respect to my target rotation with the offset, and I'm finding the fraction, 1/10 in this example, the fraction of the rotation to the target. Rather than going to finding the full full target rotation, to going to rotation to the angle, full angle, let's say 180 degrees or 90 degrees to the target, I got one fraction of it, 1/10. So instead of 90 degrees, I got 9 degrees. So that's my target. And the closer to the target, to the final target is, so closer I am to that value, this value will be smaller. So we got 180 degrees divided by 10, that's 18 degrees, because this is 1/10 of it. But if you got 18 degrees of the rotation to the target, then you got 1/10 of that. This is 1.8 degrees, much smaller steps. And I found this way actually to be best way of a number of iteration of scripts I had in the past to actually achieve the best performance of the system. And that's realistic because you can calculate what next angle you should be able, even using the physics thrusters. So that whatever your angle is, whatever you expected, your target, and what's this 1/10 of it, the nearest. Of course, it's easy to understand if you know how the quaternion works. It's like a spherical space coordination system. And then what happens is I calculate the error between my current rotation and the nearest target, so that's the fraction. So that's my error. I get my angle, so 0 to plus 360 degrees. And then when I calculate plus minus 180 degrees, so I converted that. And then I divide by 18, it's further division. So if I got 180 degrees, for example, which won't be the case, but let's say divide by 18, that would be 10 degrees. If it's 18 degrees divided by 18, that would be 1 degree. So that is now the velocity, expected velocity. If the error is 0, because I reach the goal, the target, or closer I get to the target, my expected velocity will be smaller and smaller. So as my target velocity is expected because my angle is close to the target, is applied to my current target velocity. And here is the script where those flags are applied. So I can switch between the angle or the position, the angular velocity or the angular position of the system. Typically it's target velocity. When it's false, the flags are false. And otherwise is target angle velocity. One of those. So one of those should be rather true. So I got angular error calculated based on that. So it's my current angle rather than current target angle. And based on the angular error, that's for the display, what I'm doing, I'm applying 3 inputs for the 3 axes. So they're my angles, errors, how far from the target destination I am. With those 3 inputs, what is here, I got, that's the controller. That's the neural network controller. And this is the object reference, but it got number of inputs and number of outputs. So the 3 inputs, 3 outputs, population size. Now, more complex system, you might want to have more population size, more entities. And test time, how long each entity should live before it dies. And a new generation is initiated, which we'll be going through in a moment. the other parameters here, but I'm not the best explaining those ones. A bit more explained in the paper, other resources. They mostly are okay, they're quite optimal, so they should be fine. So there is script neural network, the controller, which is just there, but barely modified, just slightly, but that's the original script, which is included in the main project of the one person, the channel group. But mainly I'm interested about the developed that script for that particular reason, for the particular case, which is this one. So I got 3 inputs and 3 outputs defined. You might change that one, it depends on the project. Then the lifetime, if it's used, if I expire, then basically after the time expires, then the object is destroyed, the object is finished. And fitness is calculated as well. So you calculate the fitness of the system. So fitness, basically, higher fitness, the more responsive system is. You want to have high fitness. So in this case, I calculate angular error magnitude. Magnitude is always positive, maybe higher value, but the 0 to whatever positive. And the 1 minus positive, so the total might be negative. So if it's negative, of course, it's, you'll be penalized, penalty applied. But if this is close to 0, so the error is almost close to 0, then the fitness will be close to 1. When you calculate the fitness, I multiply by 0.1 just for to make the graph nicely smaller, and which I'm going to show in the moment. Apply the previous angle error, applying further down, and then is the outputs. So the fire net, so that neural network is fired, is executed, and it calculates the inputs, it gets the inputs, and outputs the outputs, of course. So my array of 3 outputs, which I just been pointing out a moment ago. 3 outputs, just there. And those 3 outputs, they drive the throttles, or in this case, add relative torques to the system. So I got 3 throttles, and it can be positive and negative value. When it started this project, I might just load it. Moment, yeah, okay. You might see something like that. There's game interface, so this button which you just showed the video a moment ago. The scene of that, of course, and the scene of my little satellite and the reference target. So first I would like to, I need to load my system, I need to load my brain. I got 3 brains, but I'm gonna use the best one brain at the moment. No, sorry, I'm gonna use the brain 3. Doesn't matter, all works. Actually, my first brain didn't work as well as I would like, but yeah. I type brain 3, load the brain, create the network. So my satellite is instantiated, is populated, and I might just want to turn off the lifetime, which is not used anymore. There's an offset of 30 degrees and the 0.3 angular velocity is expected to be 30 degrees to the target. I might want to accelerate the simulation faster. So this is how it works pretty much to my offset. Or just simply I can rotate my target reference. Right, so the satellite rotates. So imagine you got that satellite which travels around the orbit in Unity3D, and you want to have always facing the same direction, the same orientation, adjusting the orientation. Let's create the neural network. So I stop it and I will open again. So I'm creating brain 4 in this case. I don't have to call it now, just I need that when I save it, but I'm not loading because brain 4 doesn't exist, but I create new one. So the new network is created. Initially you can start from the generation 1, but I'm gonna use generation 5. Actually, I found that in generation 1 you are actually finding the solution for the system. So if I got correct, generation 5, oh here we go, sorry. So I got 16 entities, population of 16 is created, each one will live 50 seconds. In this case, their goal is to reach the orientation, the applied offset of my reference point. Because 50 seconds in general is long, so I can accelerate 5 times, so that's reduced to 10 seconds. And here we go. So it's the very first generation, the solution is found, but still a few generations to go. Depends on the system, you might want to do more generation, more complex system might require more generation. This is the brain. 3 inputs, 3 outputs, so good nodes, hidden nodes in the middle, input nodes, output nodes, hidden nodes. And the system might create more those nodes. And this one actually is a nice one I found because I worked so much on it, I tried to find, and the system just behaves amazingly for me. And the performance wise is quite performant. That's when learning. So I got learn the brain, the brain 4. I want, for example, now load my brain. Oh, let's save it. So this is when it's pretty much idle. So load the brain, creating a new network. That's my new brain 4. I want to switch off the lifetime. Just adjust it to the angle. So that system responds. So that system responds in the profiler. And as you can see, when I pause, the editor overhead is the major part of the usage of CPU rather than anything else, rather than scripts. So it's very performant. So that's how it works. So we've got generating with brains. Now brains, this is referencing, in this case, in this particular project, to the file name. And in the main project file, so we got readme, which is the same file which is on very top of my script. The license, which basically is, you can do whatever you like. MIT file, which that's the PDF file with the reference I read at the beginning. But what I was interested in is brain 4. So this is taught brain 4 with 5 iterations. There was previous brain which I learned was as well good, it was a bit bigger. There's the best brain with one single iteration, which is almost the same size. And this is the brain which I had. I thought was the best one, but actually it's not. We got some flaws with this orientation with the x-axis, with the angular velocity of the x-axis. smaller brain actually is faster, as other feet are basically didn't train properly. So basically that of the system. Oh, of course, there is in the asset the scripts applied. The core scripts from the project are slightly changing naming and at the namespace. There's templating applied, angular velocity, that's the script which I developed. I removed from this project the other examples. You want to examples, go to the one channel and download the examples. In his project you could one single input boomerang and other examples you can play with those about. And I think that explains quite a bit what I wanted. Other than that, in the assets but prefabs, I just categorize it. Scene, so that's the scene, which is just materials, nothing special. In general, it's nothing special. This one actually I might remove, or it's actually not used. And yeah, that's it, I guess. So hopefully you did enjoy what I wanted to show. I think give a try, go and see what you can do with the system, what you can teach the system. This system I found it amazing. As I said, I searched for a long time. I searched the GitHub for the code, for the application with Unity, to be relatively straightforward to run, to apply, to execute, and to modify for your need. And with few lines of code, it can be working amazingly. So thanks for watching, thanks for listening to my rumble. I hope you enjoy. Bye.